So that will be our guide toward the DC. So I will try to explain as much as fast as I can. So I'll try to cover the syllabus in it. Because it's just about introduction of what Kubernetes is and everything. So first of all, for those one that are not in, maybe you don't know what Azure is, you don't know what AWS is, don't know anything about the cloud, I will advise strongly that in as much that LFS 250 is the requirement for us to use to start, I will advise you to not, you should go back to LFS 101, which is just the Linux foundation. It's very important, and you need to understand that if you know your fundamentals, you can be building on it. Kubernetes is not actually the start for new beginners in tech. You don't jump Docker, you don't jump some basics like share scripting and everything, and you say you want to move to Kubernetes. So I'll advise you whenever you have the time. The LFS 101 is long. I myself, I went through it, and I can attest to the fact that it's well jam-packed, and it will be so useful to everyone that goes through it. So going to KCNA, I'm going to start from let's start from the cloud native architecture, which is the module 2. So Kubernetes itself, let me just give you a bit history of Kubernetes and how it came to existence. Kubernetes came to is an open source orchestration platform where in the past people, they make use of what they call Docker Compose and everything, but they found out that Docker Compose was not actually meeting the demand. It wasn't too flexible, and it couldn't do some complex situations. So Google decided to come up with Kubernetes, and Kubernetes had a lot of features in it that it makes deploying so easy. So we'll talk about some of it here. So cloud native architecture fundamentals. Why is it still loading slowly? I want to explain this image to you. I don't know if you can see the image. Okay, yeah. Can you see my screen?
Yeah, your screen is visible. You can see your screen.
Yeah.
Yes, it's very visible. We can see it.
All right. So this first page now, what is really telling us is that cloud native technologies and architecture typically consists of some combinations of containers, service mesh, multi-tenancy, microservices, immutable infrastructure, serverless, and declarative APIs. I don't want to go to the technical sides. Let me just explain these two diagrams here. The first diagram here is talking about monolithic architecture, and the second one is talking about microservices architecture. Monolithic architecture, what does it mean? It means mono itself means one. So it means you are combining all the whole architecture into one, which is what is in this first diagram. And the whole architecture you are combining are the UI, the business logic, and the data access layer. For the newbies, you'll be looking at what is UI. The UI is talking about the front end. Then what is the business logic? The business logic is talking about your back end. And while your data access layer is talking about your database. Those are how your site and this thing are being made. So, hello?
Cannot tell me. Get out from here. You sit down, the two of them go out.
I don't know.
You do not know. And sit there and know. And you are there, you know. Go and arrange the shoes.
You guys have
Daniel, kindly mute. So, Daniel, you can mute your mic, please.
Okay, thank you. So that's the monolithic architecture. Why microservices architecture? What does it mean? Micro itself is trying to tell you it's minute, like it's small. So microservices means that instead of all the old components being a composite, being one, they decided to separate them and put them into different layers. So that is why you see that the UI now is in different layers. You can see all these. The reason why is that this is to help developers, because sometimes some people might be in charge of let's assume we're talking about an e-commerce website now. They will be we have a page for the checkout, we have a page for the payments, we have a page for maybe order confirmation or something. So all of these, they decide to separate each component into smaller smaller parts. So to allow then the communication within them will be more easier. And if a part is having an issue, it will be easy to debug. It will be easy to find out what part is wrong and maybe isolate that part away. But when everything is in one, you can agree with me that you have problem actually finding out which of the problem. If one has problem, definitely everything might crash at once or everything might not work together. But when everything are in fractures or in layers, you can actually remove that layer out and make sure that everything is working. So that's what monolithic and microservices architecture is about. If you have time, you can go back and read, but that's just what that aspect is talking about. Moving on, characteristics of cloud native architectures, which is the Kubernetes itself. The Kubernetes is the cloud native architecture tool. What are the characteristics? It has high level automation. The reason why they say it has high level automation is that it automates continuous integration and continuous delivery possible. What does continuous integration mean? What does continuous delivery mean? Continuous integration means whenever during the development of your application or your code, you are going to push your code to a particular source, a source code called GitHub, GitLab, or whatever. Then after you push it to that GitHub, some process will go on there to make sure that the code and everything is working fine, which is the testing, the building, the security, dependency check, and some various things. They will go on in that continuous integration just to check that, okay, this code that the developer made, everything is right. When it gets to production, it will not scatter or it will not cause problem. And what is continuous delivery? Continuous delivery is a way where whatever you build, you test, and you check everything that everything is working fine, you now deploy it to the website. Let's assume like you create an app, then you want to add a new feature. Maybe you want to add a new feature like maybe posting of image with your cat or something, but you've already deployed the new version. You deployed your old system. You want to add a new feature now. Instead of bringing all the whole site down and everything, you just do continuous integration and continuous deployment or delivery to make sure that everything on the site is still working well. Now, moving on to self-healing. One of the reasons why Kubernetes is a buzzword and is catching everywhere is because it has a self-healing. When a part of the microservices or the containers were saying, if it's bad, it has ability to heal itself. That's what the meaning of self-healing means. That when maybe I injure myself, let's just use, I don't know if you know what vampire is or something. If anyone watch vampire movie, you know that when they get injured, I think they heal automatically. So self-healing in this container orchestration means when a container is damaged, when a container is bad, the container automatically creates a new one by itself. So that's what it is. So if there's no damage in the numbers of container, if I deploy 5 replicas and one get damaged because of something, maybe a developer, a new feature was pushed and it was bad, instead of scratching everything that we've done since maybe a month ago. It will heal itself and say, okay, this container you just deployed is bad. The old one is what is going to be available. If the new one you are pushing or you are trying to put into action, into production is okay, then they will not be no, they will not, it will not reject it. I hope I'm communicating.
Sorry, please. Is that not can we say that's a form of redundancy?
As self-healing. Hello?
Hello? Did you hear what I said?
No, I didn't get you clearly.
I said, with what you explained, can we say it's a form of redundancy?
How will you define redundancy to you?
Like you said, if one Docker goes
Not
bad or
Docker,
something,
container.
it's just, container. If a
Yes.
container goes bad, it's another one picks up or something.
Yes.
Like you won't even notice that one container is down. It will just another one will just pick up and start working.
Yes. Yes.
Exactly.
Exactly.
So it's just like it's a form of redundancy, because if like it's just like for example,
I think somebody just answered
you
on the chat. He said not redundancy because to you, this is a replication model. I think that is the right word. So good Tadi, thank you for that. What my feel redundancy is something not something disturbing something, but you associating with redundancy, I don't think I accept with that. I will go with replication.
Thank you.
You can go through the chats. People are answering.
Yes, I'm going through. Thank you.
Yeah, thank you. So moving on, one other good characteristics of cloud native architecture is they are scalable. What does scalable means? Scalable means that it can increase by itself. Assume your production server, they are just 5, and maybe your target audience, or okay, there's what we call peak time or peak hour. The peak hour, Christmas period is a peak hour on an e-commerce site, because people want to buy, people want to shop online, people want to get as much as possible. So that time, if that 5 servers are actually provisioning for people in a particular period of time, the peak hours, you will not, let's say the 5 server is provisioning for maybe 30 people from January to that December, they now go to the Christmas period. That 5 server, that 30 numbers of people that comes to the site, it now increase to, let's say, 100 or 120. Then you can see that the numbers of your users have increased, and that 120 might not serve, that 5 server might not serve those 120. So a Kubernetes itself is able to see that, okay, the demands have increased. I can increase that my 5 server to 6 servers. That is the meaning of this thing. Either increase the server or increase the CPU or the memory, just to ensure availability and performance of your services. There will not be downtime. One issue NYSC website do have constantly is downtime, because the number of graduates that are trying to register on it are always more than this. That's why NYSC provisions as much as I think you have A, you have B, you have C. That's not the right way. If they were using Kubernetes will say, oh, yes, this is a peak time where everybody wants to register and we need to serve everybody at once. It's to scale itself. That's one reason why one characteristic of Kubernetes. Another thing is cost efficient. Cost efficient, in what sense is it cost efficient? It's cost efficient because it can scale up or it can scale down by itself. Like I said the other time, in peak time, it can increase up. Then after the peak time, let's say after January 5 or 6, the sales you made from December 23 to January 3rd, it will decrease. So at that time, your servers have moved from 5 to 10. And now the numbers from the 120 users have dropped to 30, and you have 10 servers. Instead of the 10 servers still working, Kubernetes will know that, oh, demand has reduced. Oh, let me reduce the server. Let me reduce the CPU memory. So 10 servers that might cost you maybe it can cost you maybe $1,000, 1,000 naira. Now it's because of the peak time is low now, and this thing it will reduce itself. That instead of you wasting that $1,000, it will reduce to maybe like 300, which is your normal cost for when everything is normal. So it's cost efficient. Using my easy to maintain is another feature. Using microservices allow breaking application into smaller pieces, making them portable, easy to test, and easier to distribute across teams. I think that will explain itself. Then it's secure by default. One essential this thing. That's why during the certification, I mentioned what they call CKS, which is Certified Kubernetes Security. You learn about how to secure pod, how to secure clusters, how to make sure that okay, everything is safe, and communication, encryption, and everything is all fine. And there's what they call 12-factor app here. The 12-factor app is a set of guidelines for developing cloud-native applications that starts with simple things like version control of your code base, environment-aware configuration, things you are supposed to be aware doing environmental configuration, and extend to more sophisticated partner like statelessness and application concurrency. So that is all for this stage. Can I move on to the next one? You have a question?
Hello? Yes, I have a question.
All right.
Yeah, thank you. Yeah, so you mentioned scaling up or down of resources depending on peak periods and the amount of demand it gets. So my question is, from where does it get the extra resources that it uses to scale up or scale down? Is it like there's a defined,
all right,
defined
that's why we're doing KCNI, and we're calling this section a crash course. So we're diving deep into how does it work, what are the components, because those are what make you a specialist. You can actually look into this curriculum and just read and pass the exam, and you won't be able to defend yourself. And when issues arise, you won't be able to know where the problem is. So I remember telling somebody who would have messaged me that it is more than just cramming. You have to understand how it works. You have to understand every component of it for you to enjoy using the tools. This is just, if it's just by reading it, you can go and do your exam and you pick A, B, C, E, J, or E, O, J, and you pass and you'll be happy. But when it comes to interviews, when it comes to you actually using the Kubernetes itself, how good will you be? How good will you know, okay, this is how I'm going to scale my cluster. This is now how I'm going to scale my cluster. So further down the course, we will explain that and how you are going to implement it. Have I answered your question?
Okay, so no problem. Thank you.
All right. Thank you. So moving on to the next stage, we have auto scaling. Auto scaling itself, I've actually, it was last thing I explained now. Auto scaling itself means the increasement of something or decreasement of it by itself. That's what auto scaling means. It means I'm doing it by myself. I'm increasing up, I'm decreasing down by myself. So there are two different types of auto scaling. We have vertical auto scaling and we have horizontal auto scaling. And this is the image for the vertical scaling and the horizontal auto scaling. Horizontal auto scaling means you are increasing the number of resources. If I have 4 CPU that is provisioning, that is helping me to do my provisioning, so maybe demand increases, and I configured horizontal auto scaling. I'm trying to say that okay, when this demand increases, increase that first CPU I have, increase it to maybe 6 or 5, or maybe the server. It could be CPU, server, or memory. That is why you can see that this horizontal auto-scaling is showing you up to 4 servers, telling you that you are actually increasing the numbers of your resources in quantity. Then why vertical scaling means you are not increasing the number, but you are not increasing like the you are not increasing the number of resources, but you are increasing the capacity of the resources. That is why here you can see the vertical scaling. What does it mean by vertical scaling? It means if I actually provision 500 MB, is it 500? Let's just say 500 MB for my CPU or something. Then maybe demand increases. It is going to move from that 500 MB to 1000 MB, which is increment in the capacity. You are increasing the capacity. You are not increasing the number of the server itself. You are increasing the capacity. That is what vertical scaling and horizontal scaling means. And if you have time, you can go through the course, but that is just the basic understanding of that. Next is serverless. So serverless itself does not mean it doesn't have server. It just means that whatever you are provisioning, it has the ability to help you save costs based on how you use it, and the provision of resources are all available. You are not the one configuring the operating system and everything. Everything, the virtual machine, the network, the load balancer, and everything, they are being configured for you by either the cloud provider or the Kubernetes this thing by itself. So that's what serverless means. And in AWS, you have different serverless services such as the Lambda, and the Azure also have its own serverless platform. So that's what serverless means. And their cloud native architecture supports serverless.
Okay. Sorry, Abayomi, please, can you comment on the serverless, with the expansion of the serverless architecture? I didn't get that.
Okay, I'll go that. Serverless means that everything you need to deploy your application, you are not the one configuring it. Like, I don't know if you use EC2 instance by itself on AWS. If you have time, you can go ahead and use it. You will notice that in your EC2, you are the one making the provision of what you want. You are the decision maker. You are the operator of it. You are the one operating. I'm not using Ubuntu. I'm using Amazon Linux. I'm not using. I want to use T3 large, or I don't want to use T3 large. I want to use this. I want to use that. You are the one provisioning. You are the one provisioning even the operating system and everything. But in serverless, all you need is everything you need for your application to do this thing. You don't need to provide it, and everything starts working for you. And when you no longer need it, you can just stop it. It saves costs rather than using normal computer or normal storage system. So that's what serverless means. I don't know if you understand, but that's that's the best thing. What do you say?
I understand. I understand what you say. Thank you.
Okay. It does not mean that it doesn't use server. It uses server, but it helps you reduce cost, and you don't provision things like the networking, the virtual machine, and everything. Everything works with it. The open standards, these are like set of defined rules that governs the operation of cloud native itself. So we have a few of them that has been mentioned here. We have OCI spec. What is OCI spec? OCI spec is talking about Open Container Initiative. That means it is more defined for your image, your runtime, distribution specification on how to run, build, and distribute containers. For the newbies, please, some of the things is just the way it is written here. I know you might be looking at what is image, what is this, what is that. That's why I advise you to probably go and do your LFS 101. And there's one that is called LFS 158. It gives you prerequisite of everything you need here. And you need to understand Docker, and you need to understand what Docker is, what image is, for you to understand what you're actually saying here. So moving on. The OCI is just an open container initiative. It governs anything that comes with the image, the runtime, and distribution specification. Then we have what they call CNI, Container Network Interface, a specification on how to implement networking for containers. That means you are trying to make the container work. Then we have another one called CRI, Container Runtime Interface, a specification on how to implement container runtime in container orchestration system. We have the one called CSI, a specification on how to implement storage in container orchestration system. And we have SMI, which is Service Mesh Interface, a specification on how to implement service meshes in container orchestration system with a focus on Kubernetes. So if you look at all this now, it's just like a guideline that what are the best practices on how you are going to do your OCI, your container network interface, and everything. That's okay. This is the best practice. If you do this, you'll be fine. Everything will be okay. That's what this open standard means. They are the general rules. As you can read in this, like, to overcome this problem, containers evolve as a standardized way to package and ship modern software. While Docker is often used synonymously with container technology, the community has adopted the open industry standard set by the Open Container Initiative. So if you belong to, if you're an engineering student, you know what they call IEE. Is a body that is actually governing the way engineers work. So this one too is a community where they actually define how things are supposed to work. Moving on, what are cloud native roles and site reliability engineering? What are the roles you work in? What are the jobs that are available? The roles and jobs are available are cloud architects. You can work as a cloud architect for a company. You can also work as a DevOps engineer. You can work as a security engineer. You can work as a DevSecOps engineer. You can work as a data engineer. You can work as a full stack developer and a site reliability engineer. With all of this, I know a cloud architect, you work with Kubernetes. A DevOps engineer, you work with Kubernetes. A security engineer, if you're interested in this aspect of security, there's a place for you to fit in. A data engineer, also a site reliability engineer, you work, because as a site reliability engineers, there are three main metrics you have to work with. Those are the SLO, the SLI, and the SLA. The service level objective, what are the target level for the service level objective, which is the measure service latency. It should not be less than 100 milliseconds. Means whatever they are doing should not be less than this 100 milliseconds. Service level indicator, it means a carefully defined quantitative measure of some aspect of the level of service that is being provided. For example, how long a request needs to be answered. And why service level agreement is just is like a bond between the provider and this thing, just like a general agreement that this is what your SLO and your SLI, maybe 99% you need to be, you need a 99% availability of your application. It should be available. So those are what SRE does. Community and guidance. I think this more talking about the Cloud Native Cloud Foundation. The Cloud Native Cloud Foundation, they are the community that actually are in charge of cloud native tools. Kubernetes is not the only one that is part of the cloud native tools. We have Argo CD, we have we have Istio, and so much more. And there are many projects they do. If you have time, you can You can go to Google, type CNCF. They have a community. They also have a community here in Nigeria, which I'm aware. Anyone that wish to join could let me know. I think there's a group link or something where they talk about how to contribute project and everything. If you go to LinkedIn, you can also search on them, CNCF. So it's a community guidance, and they are the one in charge. Though Google was the one that brought Kubernetes idea, but I think somehow CNCF got hold of it, and they are the one in charge of it ever since then. So the CNCF graduation criteria for every project, I mentioned some list of projects. They are the project they are working on. Kubernetes is like one major success story for them. Prometheus and Grafana is also a success story for them, and there are new ones that they are working on too. And what are the stages before they become a success story? The first one is the sandbox stage. This is when they are still developing, they're still testing it. Then we have the incubating stage. We have the graduation stage. All these stages are going to, every of their projects before they come to limelight, we have to pass through all these stages before they become mature. That's what it means here. Wow, we're close to this thing. So the quiz, you can go ahead and do it. We don't need to do the quiz. So yeah, we're talking about container orchestration. Yeah, the container orchestration, first of all, the first thing we have here is use of containers. Why do we need to use containers? Well, one major problem containers solve is to help make sure that when an application is built, for those ones that are developer among us, we understand that one of the major problems we face is sometimes something will work on our system. Then when another person goes to GitHub, download it, and is trying to download it and set it up, it will not work. Why? Because of dependency, the versions, and some dependency versions and stuff. So what container does is, container itself is an object that helps us to package something. It helps us to maintain it. So if I'm a developer A and I develop an application, I will have to put that application into a container to make sure that whoever is going to use it, all you need to do, I don't need to be there to set it up and tell you that, no, you are using Windows 10. Windows 10 will not work. This is Windows 11 that will work. Change your distance to Windows 11. So what the Docker and containerization the environment have done is to make sure that we can package our application, and our application can run anywhere. It can run on the cloud. We don't need to be present to be explaining and be sharing that this is the version you are supposed to use, or this thing. So it will help us package our dependencies. You can see here, install and configure basic operating system, install the core Python package. If it's not Python, it could be Node.js, which is the JavaScript, and install Python extension that your program uses, configure networking for your system, connect to third-party system like a database cake. So what container helps us to do is just to help us to package our application to avoid, I think it was written here, for example, the evolution of this one, where is it written? Although the application and dependency based, it is typically the system as well who set up the infrastructure, install dependency, and configure the environment where the application runs. This process can be error prone and difficult to maintain, which is why servers are often configured for a single dedicated purpose, such as hosting a database or running an application server. So the rest you can read it, but that's just the main information there. Container basics. So container itself, its earliest predecessor was she root, which is like, it's been old. So this is the she root structure. Like this is the parent directory, which is this slash here. That's why if you see this slash, it means home direct. It means the root directory. That's why I kind of told people to go and read the LFS 101, because you will understand better how operating system works, and you know more about virtualization, hypervisors, and everything. So let's just move on. So this stage here, well, these routes here as a subdirectories, which are the bin, etc, home, and var. This home here is talking about the users. And here we have a user called Alice. We have a user here called Bob. Then you have the tree roots, which is like a subset of these other folders being created here. That's what it means. So let's go to namespace. Some common Linux command that you need to know, which you find in LFS 101, is PID. Well, PID, what does PID mean? PID means process ID. For everything you run on your computer, it has an ID, because it's that ID you use to track it. So there's what they call NET, which is the net. That's what it's referring to in the network. We have MNT, which is mount. You are mounting a file. So it's using container basics. Another one is IPC, interprocess communication. You have users, you have UTS, C group, and time. So now, this image here is talking about the evolution that happened from the beginning. Traditional deployment itself, it works in a way where there's first of all the hardware, which is the provision of the server. Then you have the operating system. Then you have your application being built on it. So those are just 3 layers. Then they found out that there's a better way to go about it. So instead of having our application sit on the operating system, they decided to introduce what they call hypervisors. Then the hypervisors allow you now to be able to divide your application. That if you have different application now, they can use different operating system. That's why we have something like your virtual machine is the one is actually sitting on this hypervisor. So we have multiple virtual machines. So if you agree with me, with this method, you are able to deploy more apps than this, because of what they call virtual machine and their hypervisors, which gives you the ability to deploy more apps. Then they found out again that we can still do better, we can go better. That's when they created what they call container runtime. Container runtime now allow you to even make your application that you are deploying, it makes it lighter, and it makes it light, and it makes everything portable, which is what they call container runtime. So more you can deploy more application, and the size of your application are not as large as what this one will give you. And so far, this has been the best version, and this is what people have been using. And it's because of this containerization method we have what's Kubernetes. We are able to, because Kubernetes run containerized applications. So that's how we got into Kubernetes. So running containers means you use I think during the week I stated that for you to be able to participate in this, you need to download Docker and you need to download Kubernetes for you to be able to run some of these demos on your laptop. There are different ways to do it. You can do it. You can do it on your cloud platform, maybe your AWS, but that will cost you money. So you can also do it on your computer using your Linux machine. That will be so easier for you. You don't need money for it. You don't need to install your Docker, then install your Kubernetes. I hope they talked about different type of Kubernetes here. I think it's here. So let's move on. So running container. Do I need to show how to run a container, or I should move on?
Show how to run a container.
You can show us.
Okay. Let me see if I have a container. Yeah, I think I provided something here. We will say how to run a container moving forward. I think I have one here. I'll show you how to run a container. It's an Nginx container we'll run. I'll show you why we're moving. Let's just move on to this building container images. So building container images, we have what they call layers, image index, and config. All of this is more technical and won't be really won't be you can read through it on your own when you have less time, but I'll dwell more about this Docker file here, which you are containerizing a Python application. So I'm going to, for the sake of newbie, I'm going to explain what this Docker file does. This is Docker file that enables us to run that enables us to package our application in a container form. So these are the code we run. So we have from here, we have here means from Ubuntu 24.04. What this line means, this hash is you are commenting it, you are trying to describe, or you are describing for somebody else that probably is not there when you are trying to provide an information in your absence to another engineer or something. So it's always advisable whenever you do something, you comment it so another person can come and understand what you've done. So this from Ubuntu 2024, you are saying that, okay, the operating system I want to use is Ubuntu, and this is the version that I'm going to use to package this application. That's what this line means. And this one, this application here is, you are telling that run an update. If you have worked on an EC2 instance, you know that the first thing that is always advisable is for you to update the Linux server itself. So you make sure that everything is fresh. That's what update is. And the next thing is, you are telling me that get and install Python 3 and Python 3 pip on that operating system. So this ampersand sign is used to make sure that you are able, the Docker image you want to build is as small as possible. That's why the ampersand sign is. You can as well split it, but it won't. It will just be increasing. Maybe if by the time you are done and you run your Docker image, you will be seeing something like 200 MB or something. This little ampersand sign will help you reduce it by some distance. So we're going to maybe we should just run a container image and push. We can run this container image, but we need a Python app. Should we go ahead and do it?
Yes,
Yes.
Let me just ask ChatGPT to generate just a simple this thing. I have PY. Let me check. Which one should you even use? Okay, guys. is a simple just Python app. Then we are going to run a Docker file. Well, let's use the Docker file provided here. I want this to oh. Yeah, Docker file. So we have this. So let me explain that Docker file thing before we run the command. So this one, like I said is if you notice that image, this is where the operating system is. This is where this Ubuntu from Ubuntu is telling that okay, this is the operating system I want to use. There are different type of operating Linux system. So Ubuntu is the one being used here. Now we're telling Docker that okay, for us to run this our Python application, which is my app py, I want you to help us to install this. If you are into backend, you know that there are some dependencies that needs to be installed. So for your Python has to be present. If you don't have Python, your application will not work. So all these one are important for you. They are the package manager needed for it. Secondly, we are not telling this thing that okay, copy this my application, my app.py, copy it to a working to a directory called app, and here you are now saying that okay, the app I'm working on, which is the working directory, you are specifying that okay, this is the directory I want you to package my application, which is my app.py. And cmd, what does cmd mean? Cmd means the entrance for your application. That okay, if you want to run an application, you always write python 3 my app.py to run the application. So you are making Docker understand that okay, this is all I need. And please, before you start running, you need to check for that Docker is present on your system. Don't come at me and tell me that it's not working. You have to do Docker version to see that okay, yes, I have Docker. And also, if you check your system, you can do Python version to also check if Python is available. Your Kubernetes too, if you download it, you can also check Kubernetes, your Kubernetes version, but we're not yet in Kubernetes version. So now, the first thing, after you've installed your Docker on your machine, you cannot build the image. That means you are trying to package the image. Then you now for you to package the image, you use this command line, Docker build. So this command, let me just quick explain it. The build is you are trying to package the application. This -t means tag. That's this, you are tagging that thing that you are building. You are tagging it as my Python image. You can tag it whatever. You can tag it your name. You can tag it your son name. The reason why we tag is for easy identification. Then -elf is now telling us that the file name Docker file. That is what I want you to work with. That is why if you check our application here, you will see I name a file here called Docker file. Then you click you when you run the code. What is this? Start a build. Docker build this thing. The command requires build sf. Okay, Docker build. Let me just use ChatGPT to debug this issue on time. So we don't waste time. Docker is installed now. Oh, I think the code available there, is it bad? Docker build. Okay, the working directory. You have to put dot to it. What? Why? Oh, I have to follow my Docker. Yeah. Please give me a second. Let me pull on the Docker application itself. Okay, I think. Let me try. Now you can see that the application is building by itself already. We're packaging the application. If you have time, you can read it. The whole packaging of the application is already working.
Hello, sorry, please. We cannot see the app running on your screen.
The app or you can see my terminal.
Yes.
Just show your browser.
Sorry, I didn't hear you.
It's only showing your browser. We're not seeing.
You can see my browser. Should I make it black?
But we can see your browser,
Okay,
but we can't see the terminal.
Oh, you can see my terminal. Oh, let me reshare the screen. Can you see my screen now?
Yeah, we can see your screen. Okay, I
Can you see the terminal?
Yeah, we can see the terminal.
Let me. Do I need to start the process again, or I should move on?
Just move on. Just continue.
Okay. So let me build the. I've created the Python file, which is a sample file, just an hello word. Then I also wrote a Docker file for the packaging of the application, explaining to the Docker server itself, because we have 3 components of Docker. We have the Docker server, we have the Docker hub itself, and and there's what they call Docker daemon. Those are the 3 components. So the Docker server is the one that handles your API requests, and the files it's recognized as Docker file. So we are trying to build our image, we are trying to package it, and Docker hub is, how would I put Docker hub? Docker hub is a store where you push your image into. There is a storage for saving your images. Whatever Docker image you have, you can save it on the Docker hub. So it's like a storage form. The way GitHub is where you store your code, you can go ahead. Docker hub is also for storing images. So if this image I'm building now, that I'm packaging, when it is ready, there's what they call Docker push. I'm going to push it to the Docker hub or any container registry. There are different types of container registry. You have different type of containerization. We do Docker is the most popular one, but we have various ones. We have Podman, we have a lot, but all of them they work the same way. So, but Docker Hub is the most popular one. So when you create an application, you containerize it, package it, then you push it to Docker Hub. Anybody in Nigeria or in Japan or anywhere, they can just go through get the image of this thing, pull the image from the Docker Hub, and this is Docker Hub itself. I don't know if you can see it. So these are some of the image I work on that I actually push here. Then there are different type of open source image also. There are different type of image to always available on open source. I have to sign in, but I'm not ready to sign in right now. So while we are waiting for this, I think we should move on.
Sorry, boss.
I
Please,
don't
I
know
have
if
it. Sorry,
Okay.
can you hear me, boss? So,
Yes, I
can you hear me?
you.
So you mean
Yes, sir.
when we finish a package on Docker, the total package is
Yes.
called an image, right? Because I'm trying to
Yes,
figure
sir.
out what is called an image in the Docker file.
Yes, it's called image. Yes, sir. You're right.
Okay. Okay. Thank you. Good job, boss.
Okay. So let's move on. So that's how it takes some time for it to complete. When it's complete, to let you know. So maybe before we're done, building container image. The video is also here. You can go ahead and try it on your system if you have Docker installed. We have security. You have security. So security of Docker, there are different that type of practice you need to follow. If you click on this blog link, top 20 Docker best practices, and in terms of containerization, there are 4 layers you focus on for your securities. And wait for this image to get ready. There are called 4 C's. The first one is container. You have to make sure that your container is secure, because if your container is not secure, all the application of your company is at risk, or whatever you build is at risk. Because just going to your Docker Hub and they get the image, they can download it to work on that system. So security of your container is important. Your cluster itself is important. Your cloud data center, the security also is important. That is 3. And I think a main one. The one is, I'm waiting for this image to. I can't remember the one. If anybody know the one, you can actually add to it. I think it's up to 4. But I can't. My image is not loading. Let me refresh. Network is bad. Okay, yeah. So if you check this image here now, you will notice there are 4 these things you have to be so aware of. Security of your code, the container security, you have to be aware of it. The cluster, which is on your Kubernetes itself, you have to be aware of it. So that is where Kubernetes security engineers are needed. That okay, all these are our applications we build. You understand on how we are going to secure our cluster, everything, every loophole for hackers to penetrate. You will be in charge of everything. And the cloud data center, you're not the one in charge of this. AWS, Azure, GCP, Oracle, they are the one in charge of your cloud data center. So if anything happens, I think they'll take the responsibility. Container orchestration platform. Container orchestration platform, it means, okay, these are our containers. We have multiple containers we want to operate, want to work with. how do we make use of those containers at the same time? That's where container orchestration platform comes in. And before Kubernetes came, there's what they call Docker Compose. Docker Compose is a container orchestration platform that actually helps you to run multiple containers at the same time, providing your CPU, your memory. You manage all the containers. It's also manage the networking, the storage, and everything. Everything will be working perfectly. But the Docker Compose, it has a limitation. It doesn't have ability to self-heal. If a container is bad, it's bad. It's bad. It cannot heal for itself. Auto-scaling, Docker Compose is not so smart like that it can auto-scale for you. So that's when Kubernetes, which is a container orchestration platform that allows you, that has more ability and capacity than what Docker Compose is. So if you read this last line, you see why several orchestration tools have existed over the years, most have faded in relevance. Today, Kubernetes emerged as the industry standard for container orchestration, offering powerful, flexible, and scalable management for containers, for containerized applications. So that's where Kubernetes comes in, because of different abilities and more robust works it can do. Moving on to networking. Microservices architecture relies heavily on network communication. Unlike monolithic application, each microservices exposes an interface that other services can call. For example, a service that returns a product list of an e-commerce. So to save ourselves reading, what do I understand by this microservices architecture of networking part? It's telling us that, I told you guys that the microservices, you are dividing applications into smaller parts. And so, and those smaller parts you are dividing it to, you are making them talk to each other. And what better way can they talk to each other is by them having an IP address, which can improve communication. My brother that does Cisco here knows about that. So now container network now means each of your container of each servers, they can communicate with themselves. That communication is what gives Kubernetes some of the ability that we all know today, that containers can discuss with each other, and they know that, okay, well, maybe container, this last container here, which is 192.168.117 is bad. We know that, okay, for the time being is bad. When another one comes up, he will have his own IP address, and there's a place where all these IP addresses are stored for that communication to be easy. So Kubernetes best ability is automation. It automates itself, and that is why it is called industry standard right now, because it has everything for you to automate itself, for you to know that, okay, I need to assign a new IP address to this container. I need to do the route traffic to this container. I don't want to go deep down to what they call service mesh, blue, green, and all those. So right now, this is an host network. We have server A, which is 172.16.4. It has its own container. Server B also has its own container. Server C also has its own container. So container network, this IP address is what makes communication easy for them. Now we go into what they call service discovery and DNS. DNS is called domain name service. In traditional data centers, server management was relatively simple. Many system administrators could even record the IP addresses of key systems for memory. So what this is just trying to tell us that one of the characteristics of Kubernetes is service discovery and domain name service. If you check that last image we saw different server have different container with different IP address. Because of we're handling so many containers with different IP address, we ourselves we cannot remember all of those IP addresses. So that's why Kubernetes, the ability to be able to identify those containers and those IP addresses is what they call service discovery. And those service discovery, the DNS here is talking about, okay, when we identify all of those containers, we can associate them under one name, one domain, which is maybe amazon.com, maybe yomes.com, all of your IPs. That's why I said the microservices architecture, maybe the different containers, maybe container A now is the checkout page, is the checkout application. Container B is the other page. Container C is maybe the front end. So if you are trying to access amazon.com now, because they are in different container, Kubernetes can itself receive your request and know that, okay, I'm taking you to the front end of the page. After you pick, which is the cutting page. After you pick, I'm going to direct you to the other page. So microservices architecture allow those components talk to each other effectively. Everything is working fine. And if you remember the first picture we start where we divided the monolithic and the microservices architecture, you could see the microservices doing different forms. So this is what the model DNS servers with service API can automatically register new services as they are created. This method is straightforward and widely adopted, as many organizations already use DNS servers that support this ability, these capabilities. Let's check our Docker image. So if you notice now, our Docker image has built successfully. So we can actually check. I don't know the name we name this is the tag we tagged our Docker image. So let's just see if the image is ready. Yeah, Docker inspect. Let's inspect this. So this is the Docker image. I want to get this is the Docker image we built. The ID, this is the ID. This is the my Python image. We can actually get the size of the Docker image. Let me pick the command here. I want to pick the command of this thing to confirm the image. Image ls. So these are my applications. If you notice now, can you see my terminal? Hello.
Yeah, you can see your terminal.
Yes, you can see your terminal.
Okay.
Yes, you can see your terminal.
So if you do Docker image ls now, you can see that the image we built is actually my Python image, latest 6
Sorry, can anyone still hear about me, or is it just me?
No,
It's not just you. It's not just you. I
I
can't
can
hear
hear
you
you.
too.
Hello, sorry, my internet went down. So I think we should, it's past 8 already. We should just do extra 15 minutes and, or what do you guys think?
Maybe we should go and digest what we learned today. I don't know. Just a suggestion.
Okay. Should I be just finish this part, these three, then we'll start the Kubernetes fundamental because now it's just about the basics of container.
Yes, please.
Okay.
Yeah, let's finish and start the Kubernetes fundamentals.
Okay. So the image you created the other time. This is the output here on Docker Hub here. So
I can see your screen.
You can see my screen. Oh, sorry, I've not shared it. Can you see my screen now? Can you see my screen now?
Yeah, we can
Yes.
see your screen.
Yes,
Okay. The Docker image you created the other time, this is it. 508.87 MB. And this thing, if you check here, this is it here on our terminal. So assuming after creating this image, what I'm supposed to do next is to push it to Docker Hub, and whoever needs it can download it and it work perfectly. Everything I've already packaged the app, the operating system version, the dependency, and the package manager. Everything is in the Docker Hub, so there's no issue of it's working on my system. It's not working here. That issue is solved. So moving to this to the next part. Okay. Moving to the I don't know, this service discovery and DNS. I think I've done justice to that. Or should I continue?
You've done justice to it.
Okay. Yeah. Service merge. This one actually took me a long time before I could understand it. But I think right now I have a good knowledge about it. So what service merge does is it allows you, it extends, a service merge extends this concept by automatically deploying a lightweight proxy alongside every container in your system. These proxies handle all network communication between services, abstracting away complexity for application code. So what the service mesh is helping you to do that. Those are your containers that you are running. They have what they call services. You will not some of you, except those that have read the course and understand what is this thing, you know what services means. The service is a networking aspect of the Kubernetes that connects, that maps to our IP addresses, to the container IP addresses, because when a pod receives an IP addresses, that IP addresses cannot be used for communication. It has to be connected to this service. So when traffic is coming or a request is coming from the outside world, let's say Amazon.com now, it goes through some processes. So the processes it goes through is that it comes to its the service, which is this service will now say, okay, we service say, oh, I'm up to IP addresses of 192.68 to something, then it now talks to our container, which is our Docker image. I don't know if you get what I'm saying. So what service mesh does is that it's with that container, there's another container that runs alongside it that helps us to secure our container to make sure that the traffic that is coming is secured and it can be distributed, and it enables communication between different services, like services A and services B. Example of service mesh the Istio, which I told you earlier, is part of the CNCF project. So the Istio now, the service mesh now is divided into two: the control plane and the data plane, just like our Kubernetes too. When we get into the Kubernetes we'll notice that Kubernetes service is divided into two components: the master plane and the control plane. The control plane and the worker node. Why this one is master plane and the data plane? So this data plane now, this is where each of our services is working with our proxy. So you will notice now, this is what they wrote an arrow here, which is signifying ingress traffic. That means the traffic that's coming from the outside world. Maybe Mr. Yakubu now wants to eat the service. This is the traffic that the request that is coming is going to hit this proxy before it hits this service, which is your container that is mapping, that has the IP address of your container. It's going to hit this proxy. So when it hits this proxy, the proxy will not hit service. So communication is not going on between Mr. Yakubu that is here and the service. Communication is passing through the proxy, then hitting the service, which is making the communication secure. Mr. Yakubu cannot hit service A. It has to go through the proxy. And what is proxy? I don't know if anybody can help us define what a proxy is, so we understand it a little bit.
A proxy is a server that you it's kind of like a read, like it will relay the traffic to the main server that is being accessed, and then still relay the traffic from the main server back to the end user.
Okay, thank you, sir. So we can understand that. So that's what a proxy is like. Is an intermediary between the server and the end user. So it's protected. So the server is being protected. That's how an example of a proxy is a VPN. Because a VPN protects a user location or distance. So a VPN is a proxy that actually is kind of marks it. So that's why we have a proxy here. So this proxy now is talking to this service A, and this service A can communicate with service B. That's where our microservices architecture can communicate, because of the ability of what they call service mesh, which service A can communicate with service B. That's why the different decoupled services, they can communicate with each other, with one another, because of the help of what they call service mesh and mesh traffic. And here is the traffic that is going away from the proxy is called egress traffic, which is called outbound traffic. So we have different types of service mesh. We have Istio mesh. Istio mesh is a very popular type of service mesh, and another one that another organization also uses is called Linkad. So depending on the organization, I think both of them, they do the same thing, but people have their preferences, and some have some extra abilities that make people choose them. So, but the way their function and their responsibility are the same thing. So your service mesh is in two layers, which is the data plane and also in the control plane. And if you are to understand what my brother said earlier, is this dedicated server application sits between the client and server to manage, filter, or modify network traffic. Common example of a proxy is Nginx, HA proxy, and Envoy. They are example of they are example of good proxy or load balancer, because they forward traffic and also reverse traffic at the same time. Then this is the last one for tonight. We have the storage. So the storage are in different layers. Then we were talking about your image, and this 188.1 MB is talking about your size. It's talking about the size of your image. This D3AA, this thing, is talking about the ID. So that is why if you check our image that we created, if you click on this thing, there's an ID to it. Let me click on it. There's an ID to it. So you can see the layers of your Docker image that you actually built, which is, these are the layers: the working directory, copy my app, and it was rightly so you can see everything here is called image layers here. Then based on your Ubuntu, which is your Linux terminal, Ubuntu 50.04 image, then is called the container layer. Then moving down, I think this directory is talking about volumes, sharing host volumes. So here we have container A, we have container B, and data here, data is being stored in this folder. For different containers now, his own volume of information is stored here. For this container, his own volume is being stored here. So collectively, everything is stored here. So that's how containerization is able to work. This host data now, it has been partitioned already to contain different data for different containers. Then this one too is actually speaking about that. Then I think the next time we'll have meeting, I don't know, should we make it tomorrow? Should we make it Sunday? So we can go into the Kubernetes itself. Time is fast gone, and I have to go and watch my report.
Thank you, boss. I think Sunday will be okay. You know what my research.
Catchy.
We should go to the WhatsApp group.